When we're given a system of equations, we really want to ask, are my equations different from each other? Or are they linearly dependent, or they're linearly independent? So independent means they're different from each other. Dependent means at least one of them is the same as another one. So there's a couple ways we can go ahead and figure out if our equations are independent or dependent. The first way is to essentially do the same thing that we did for linear combinations. So this here is the definition of a linear combination. So we set it up as a linear combination and we solve for our constants. So that's what we do, solve for constants. If all of our constants are 0, that means they're linearly independent. That means our equations are different from each other. If some of the constants are non-zero, remember only one of them needs to be non-zero, then they are linearly dependent, which means at least one equation is the same as another, or the others, or some combination of the others. Essentially, it means there's one equation, at least one equation, that gives us no new information. So I'm going to talk about span in the next video. But that's one of the ways we can go ahead and figure out if our vectors are linearly dependent or independent. We set it up as a linear combination. We can also figure out if our vectors are linearly dependent or independent using something called the rank of a matrix. So the rank of a matrix can be determined by putting our vectors or equations. Remember, we think of equations as vectors. We don't need to incorporate the b vector for this. You can, but you don't need to. But put vectors into a matrix and reduce it to row echelon form. So this is essentially Gauss elimination. Gauss elimination. The number of non-zero rows after REF is found is the number of linearly independent rows or columns in the matrix. It doesn't matter if they're rows or columns. It's still the number of linearly independent elements or rows, columns in the matrix, which tells me how many linearly independent equations that I have. There's also a MATLAB function called rank that you can use. So one way we can find linear independence is using a linear combination. We can also find linear independence using rank. So here's our process for rank. Create a matrix with the vectors of our equations, our vectors equations, as rows or columns, doesn't matter. Generally, we put them as rows. Use row operations to reduce to REF, and then the rank equals the number of rows that aren't 0. So if there's 3 rows that aren't 0, that means there are 3 linearly independent equations or independent vectors in that matrix. If the rank is less than the number of rows, so if I end up with something like this, where my rank here would be 2, if it's less than the number of rows, which is 3, then my vectors are all linearly dependent. And we can use this, just like we have in the past, in order to figure out how many solutions we have for our system of equations. So essentially here, we're saying, go ahead, set up the augmented matrix, do Gauss-Jordan elimination, or Gauss elimination, or Gauss-Jordan, doesn't matter. Do Gauss elimination, so get it into REF, and then our solution, once we get it into REF, tells us what kind of system we have and how many solutions we have. You did this already in homework 10. So if the rank of A, if the rank of just this side is equal to the rank of both sides, of AB, then this system is consistent and has one solution. And that's where we end up with a lower triangle of zeros and then values over here. That is our consistent solution, consistent system, one solution. If we end up with all zeros along the bottom, then the rank of A equals the rank of AB. So here's A, here's AB. So the rank of A equals the rank of AB. It's both 2 in this instance, but it's less than the number of unknowns or less than the number of columns. Then the system is consistent and has infinite solutions, and we already know that. And then lastly, if the ranks differ. So if the rank of AB of A is less than the rank of AB, then my system is inconsistent and no solution. Keep in mind, if I end up with this situation, this is consistent with one solution. The rank over here is 3, the rank over here is 3. Okay, so that's different than if there was a 0 here and a number here. This here is inconsistent, no solution. So that's our second method in order to determine linear dependence or linear independence. Find the rank of a matrix, and here's what it looks like in the context of solving a system of equations. The last method that we can use in order to determine if our vectors are linearly independent is, if we have a square matrix, is to find the determinant of the matrix. So remember, if the determinant is not equal to 0, then A inverse exists. But if the determinant of A is equal to 0, then A inverse does not exist. Which tells me that here I have no solution. Here I have, well, not necessarily no solution. I have no solution or an infinite number of solutions. And here it tells me I have one solution. And we'll see what that means later. So essentially what we can do is we can go ahead and if we write our system in the form of AX equals B, and if A inverse is not equal to 0, then automatically our vectors are linearly independent. So if A inverse, or determinant of A is not equal to 0, then my vectors are linearly independent. If it is equal to 0, then they are dependent. So those are our 3 methods in order to find out if our equations are linearly independent, if they're different equations from each other, if they all have different information. Find a linear combination, solve for my constants, put them all in a matrix, find my rank, or if it's a square matrix that I end up with, find the determinant.